All right, let's now explore the conservation laws that apply in particle reactions. And let's start first from electric charge conservation, something you should be familiar with. So as you know, the electric charge must balance between the initial and final states of a reaction, as has been assumed in chemical reactions, probably in your chemistry class, and in nuclear reactions. For example, a neutron cannot decay straight to a proton, but it could decay, for example, to a proton and an electron, which then balance the electric charge to be neutral as the neutron. And you can add any neutral particle there with it as well, since it does balance the electric charge. Now, why there's that third particle there, this other neutral particle, that's a different story, which we'll come to soon. But other examples illustrating charge conservation can be shown here. For example, you could have a reaction combining a positron with an electron. They could scatter and produce a positron and electron again in the final state. Maybe they just did a Coulomb scattering. But you can't have a positron and an electron come together and make two electrons. On the left side, you'd have neutral charge, a plus and a minus, which would balance to zero. And on the right side, you'd have twice the negative charge of the electron, and that is not conserved. Or another example, let's say you're colliding protons, they're positively charged. You could have two protons make a scattering and lead to two protons in a final state plus another proton and antiproton. You have charge plus 2e on the left side, you have 2e here, and then e and minus e from the antiproton, which has opposite charge. So that conserves electric charge. But you can't have two protons combine to make a single antiproton and the two original protons. You need an extra proton there to balance the charge. Now, a more subtle case would be this one. A neutral pion, which has no electric charge, does decay, and it decays into two photons. But why doesn't it decay into a single photon? They both conserve electric charge. Well, that leads us to the next conservation law, which is that energy and momentum have to be conserved as well. And in particular, in relativistic physics, and there is a relativistic description that includes quantum mechanics to describe particle interactions, both energy and momentum are always conserved. And basically that means that, for example, a nuclei cannot decay if the mass of the final state products is larger than the initial ones. You would have to add energy somehow in a reaction to create the extra mass. For example, a decay that cannot take place in free space is a decay of a proton to a neutron plus a positron. That's an anti-electron. It does conserve electric charge, but the trouble is the neutron is more massive than the proton. So if you were in the rest frame of the proton, it would violate energy conservation because the mc squared of the proton's energy in the rest frame is less than the rest mass energy of the final state products. So where did that extra energy come from, right? So it can't decay that way, which is probably good for us that the proton doesn't decay, right? All right, reactions could proceed, however, provided that there's enough initial kinetic energy in the collision products. For example, I could have a positron and an electron collide and annihilate into energy and then create outgoing a muon and an antimuon, a mu plus and a mu minus. Even though the muon's mass is 207 times the electron's mass, if you have enough kinetic energy in the collision, that energy can become mass in the final state products. So reactions are different, depends on the incident energy. Now, the reason, coming back to the original question posed on the last conservation law, the reason the pi zero can't decay to a single photon is because momentum would not be conserved in that case. Why? Well, in the rest frame of the pion, you cannot have a photon at rest. They always travel at the speed of light. The pion itself, though, cannot reach the speed of light because it has mass. So in one case, you have a rest frame of the pion, where it's not moving in that rest frame. And if it decayed to a single photon, how would that work? The photon has to travel at the speed of light in any reference frame. So it doesn't work unless you have two photons whose net momentum sum would then be the momentum of the initial pion. So it takes two of them to conserve momentum. That's one way to think about it. Okay, but there are more conservation laws that have been determined experimentally. Let's talk about the next one, which is baryon number conservation. And what do we mean by that? The proton and neutron, but also a whole collection of particles called baryons, and these are hadrons that are fermions. So in other words, all particles that feel the strong nuclear force, but have half integer spin that's a fraction of h bar, like 1/2, 3/2, and so forth. Such baryons have a quantum number associated with them that is apparently conserved, and that is called the baryon number, which we'll label just B. And we've come to this conclusion because it's the only explanation we can come up with why the free proton is stable, which again is a good thing. Otherwise, all matter, all atoms, all nuclei are suspect. They could decay. But the universe has been here a long time, so the free proton apparently is stable, with the lifetime measured to exceed 10 to the 30th years from experiment. So in other words, it doesn't decay, for example, a proton into a positron, that's an anti-electron, plus a pi zero. The proton has enough mass to have that reaction go. It does conserve electric charge, it does conserve momentum, but it doesn't go. And so therefore we assume that there's a quantum number attached to the proton, and in fact to all particles like the proton, including also the neutron and other baryons. And baryons will have this quantum number equal to +1. If you have an antiparticle or an antibaryon, then its quantum number would be the opposite. The baryon number would be -1, and would require the total baryon number on each side of a reaction to balance. Okay, and the reason it doesn't balance in the equation above is the proton would have baryon number 1, but the electron, or anti-electron I should say, is not a hadron, so it would have 0, and the pi 0 is a hadron, but it's not a baryon. It has integer spin, so it'd be 0, and so those don't equal. Okay. All right. But we could think of another decay, and that is the decay of a particle known as the delta plus plus, a doubly charged hadron. And in fact, it's a baryon. So that is a baryon, and it does decay into a proton and a charged pion. Proton has charge plus E, and the pion, pi plus anyway, has charge plus E, so it conserves electric charge. The delta is a spin 3/2 baryon. So since it's a baryon, it has baryon number 1, right? Well, so I can write it over there, 1. The proton, as I've introduced, has baryon number 1. And the pion is not a baryon, it's a meson. So I'd have +0 here. And that does equal. So baryon number is conserved. Okay. All right, so that covers baryon number conservation. If you have a baryon on one side of the equation, you better have one on the other side. And be careful, because if you have an anti-baryon, like an antiproton, you would have a -1 unit of baryon number. Now let's talk about some other decays. In particular, let's talk about beta decay, where, for example, a nucleus can emit an electron and one of the nucleons can change. So it turns out that propagates by the weak nuclear force, and it is responsible for many of the radioactive decays of the elements via this beta decay, which is, as you know, is electron emission. For example, when we discussed nuclear reactions, we could have carbon-14 decay to nitrogen-14 by the emission of an electron, which conserves electric charge and energy. Inside the nucleus, this is just the decay of the neutron in the carbon nucleus to a proton plus an electron. So it doesn't change the atomic mass, but it does change the atomic number from 6 to 7 because we've increased the proton count by 1. However, there's a subtlety here. The way I've written the reaction, there's only 2 final state particles, the nitrogen nucleus and the electron. And if there are only 2 decay products, the decay electron should be monoenergetic. That is, they have a single fixed energy, the electrons emitted. basically in the rest frame of the nucleus, the carbon-14 nucleus, when it decays, I must have two outgoing particles traveling opposite directions which conserve the momentum. So they have to have equal and opposite momentum. Doesn't necessarily mean equal and opposite energy, but at least momentum has to be equal and opposite. And if you work it out and actually solve for the energy momentum conservation, you'll find that the electron energy should be equal to the mass difference between the neutron and the proton. So there is a slight mass difference, 939.57 MeV for the neutron, 938.27 for the proton, leaving a net energy, and that's a total energy for the electron of 1.3 MeV. With the proton picking up a small amount of energy, a small amount of kinetic energy in that balance of energy momentum. So I've kind of approximated here that the electron has pretty close to 1.3 MeV. However, this is not what's observed. It's not a monoenergetic electron with a single fixed kinetic energy. Instead, the kinetic energy of the electron shows a range of values, not a single value, that qualitatively looks like this diagram here. So if I plot the energy along the horizontal axis and then the distribution or the probability of what energy the electron will have, it is a distribution. It is not a monoenergetic spike at 1.3 MeV. Is momentum not conserved? So a monoenergetic spike, by the way, would look like spike, say, at a certain fixed value at the end of the spectrum there. So if there's not this monoenergetic spike and it's a distribution for the electron energy, does that mean momentum is not conserved? That would be a crisis in fundamental physics, right? We've always told you momentum is conserved. And so it was up to Wolfgang Pauli, who proposed an explanation to avoid this crisis. And in fact, he wrote it in a note or a letter, if you like, to a conference back in 1930. And he explained that there's another particle involved in this decay. And this third particle is now called the neutrino, as a term coined by Enrico Fermi, which in Italian would essentially mean little neutral one, in the decay. So we don't have a decay of the neutron to just a proton electron. It has to have this neutrino there involved as well here, this guy. And so we've added a new electrically neutral particle that had not yet been detected. So it was a very bold prediction. When you haven't seen such a particle, to just add one. And that was the fix to make energy and momentum conserved, which might seem a little suspicious if you've not seen that particle. However, it has indeed been seen. It took many years later, until 1956, when enough neutrinos were produced from a reactor so that it can be directly detected in an experiment done by Cowan and Reines. Okay. Oh, there's my monoenergetic spike. So let's talk a little bit more about that neutrino. So the neutrino has no electric charge, as I've just said. Otherwise, the reaction wouldn't have balanced. It turns out it is a spin 1/2 particle like the other leptons, like the electron. And it has, well, it was assumed to have zero mass, but it turns out it does have a very, very small mass, nearly zero mass, but not exactly zero. And in fact, if we looked at angular momentum rules about how the spins add, in fact, we would have also concluded that we needed a third spin 1/2 particle. We had the neutron decaying to a proton. They're both spin 1/2. The electron spin 1/2. But on the right side of the equation, I need one more spin 1/2 particle so that the spins add and can make the spin 1/2 neutron that you started with. So there's a couple of reasons why you'd be led to this neutrino hypothesis. Turns out the neutrino is stable. It doesn't decay. And Enrico Fermi, the physicist who coined the term neutrino, he developed a theory of beta decay around this, basically a theory of the weak nuclear force. So this neutrino, since it has no electric charge, does not interact via the electromagnetic force. It's like the electron, so it's a lepton. It doesn't interact with the strong nuclear force. So what's left? Well, just this weak nuclear force and gravity, but gravity is very weak and the mass is very tiny. So really it's only the weak nuclear force which is contributing here. Because of this, and because the weak force is so weak, the neutrino is very penetrating. You would have to produce large numbers of neutrinos to have a chance to detect one. In particular, the only way you have a chance of producing such large numbers of neutrinos is, as I said, you can put your detector outside of a nuclear reactor where there's neutrinos being emitted in those reactions that have beta decays in them. Or look at particles from our atmosphere. Cosmic rays collide with the upper atmosphere, create showers of particles, and some of those are neutrinos. Or the sun itself, the largest fusion reactor we have in our solar system. And it emits a lot of neutrinos as well, and those have been detected. Okay, now, given that, let's talk about the decay of the muon. The muon, which used to be known as the mu lepton, but got contracted to the term muon. Let's talk about how we could write its decay, because it's also unstable. It surely should yield monoenergetic electrons, right? Because I've got a muon here, negatively charged, decaying to an electron, negatively charged, and I can add the neutrino there as I might need. But actually, no, that's not enough. The electron energy is not monoenergetic still. Even though this looks like a two-body decay, so the electron should have a fixed amount of energy, it's not at all. So what's going on? Well, we come to the conclusion that neutrinos have to come in different types. Or to use the proper term in particle physics, they come in different flavors, the proper scientific term for type. It's pretty silly, but in fact, that's our term for different types of particles that are of the same species. So the actual reaction for a muon decay, the mu lepton, is that it decays to an electron, and there are two neutrinos in the final state, an anti-electron neutrino and a muon neutrino. So there apparently is a neutrino associated with the electron type and a neutrino associated with the muon type. And even more so, there's neutrino flavor type corresponding to each charged lepton flavor. And so there's one for the electron type, the muon type, and we didn't discuss it here, but there's a heavier charged lepton called the tau lepton, and it has a neutrino type as well. So, a little bit complicated, but let's see how we can put this all together into a conservation law. We're going to introduce the quantum number concept known as lepton number. We say that leptons carry a conserved quantum number, referred to as this lepton number. And an electron or an electron neutrino on one side of a reaction must be balanced by the same number on the other side of the reaction. But the same is separately true for the muon and muon neutrino in the reaction and the tau lepton and tau neutrino in the reactions. There's three lepton numbers in total, an electron lepton number, a muon lepton number, and a tau lepton number. And each lepton flavor has its own separately conserved lepton number, Le, L mu, and L tau. Antiparticles, just like for the antiparticles of baryon number, antiparticles have negative lepton number. So an anti-electron would have the opposite lepton number of the electron itself, which is negatively charged. So let's see what's going on in the decay of a muon into an electron and two neutrinos, one of which is an antineutrino and a muon neutrino. Let's analyze this in terms of this lepton number and see if it's conserved. First, we can start with the electron lepton number. So the muon is not an electron. So its electron number on the left side of the equation is 0. The electron, of course, is an electron. So it has electron lepton number equal to 1. Now, there's an electron type antineutrino. So it does have electron lepton number, but because it's an antiparticle, it has -1. as its lepton number. And the muon neutrino, well, it's a muon type. That's a separate quantum number. It's not an electron type, so it's 0 in the electron number. So does 0 equal 1 minus 1? Yep, sure does. What about the muon lepton number? Well, I do have a muon in the initial state, so we'll say that lepton number equals 1. The electron is not a muon type, so it has muon lepton number, 0. The electron antineutrino, again, it's not a muon type, muon lepton number 0, but the muon neutrino does have muon lepton number 1, and 1 does equal 0 plus 0 plus 1. So that works out, and that's the explanation. But let's look at the third lepton number, and we can look at a different reaction. We could look at the decay of a tau lepton, let's say the tau minus. It will decay to a muon, say a mu minus, emitting also 2 neutrinos, an anti-muon neutrino type and a tau neutrino type. We can see how this works. Let's look at the muon lepton number. Well, a tau is a different type of particle. It's not a muon type, so it has muon number 0. The muon, okay, that's the muon type. It has muon lepton number 1. The neutrino has the muon flavor. Since it's an antineutrino, will have the opposite muon lepton number, so it'll be minus 1. And the tau type neutrino, well, that's not a muon type, so that's got muon lepton number 0. And indeed, 0 on the left side equals 1 minus 1 on the right side. So muon lepton number is conserved. What about tau lepton number? Well, the tau lepton, sure enough, has tau lepton number 1, and the muon is not a tau lepton type, so it has tau lepton number 0. The muon neutrino or antineutrino also has tau lepton number 0, but the tau neutrino type does have tau lepton number 1, and so that works out. Okay, we will continue on with our conservation laws in the next lecture.